Let's begin looking at some examples of hydraulic systems. Here I have example 1 and 2. I'd like to start off with these two basic problems. The classic emptying tank, that is a problem that you've probably seen maybe even since high school calculus classes sometimes, and then the cascaded tanks. Obviously they're very much connected. But it gives us an opportunity to again review some of the basic ideas behind the model elements that we'll use. Now, when you're looking at this system as compared, for example, to an electrical system where it's really clear, here you do have to make some kind of decisions. When we call something a tank, right? We're usually saying that we're making an assumption about it being sort of a vessel that can hold water as opposed to a pipe. So, I like to use this example in contrast to, say, if you had a tank that was long and thin, because in this case, we like to think of a tank as being sort of a wide aspect ratio. So the water, if you think about it, the velocity is falling at a relatively slow pace such that you can make the assumption that the hydrostatic pressure at the bottom of the tank here is rho GH. And when we make this assumption that it's quasi-static, it means that we don't have any dynamic pressure down here, right? So now we've got this symbol here that I'm going to use to represent sort of flow through an orifice. It's going to mean that it's a short section, or maybe even just a hole in the tank. So this is offering some resistance. So we really have just sort of a capacitive type, hydraulic capacitive element, and really some resistance to the flow. And if you think about it, the pressure out here is atmospheric. Pressure out here is also above is atmospheric. So when we talk about the pressure here being rho GH, we're talking about a gauge pressure, right? So how do we go about modeling this system? Well, what we can do here, we just rely purely on classical approaches. We really are just looking at this as a control volume, and we can then think of the fact that we do have some volume stored here, and there's also some flow leaving. We can also go ahead and say, oh, there may be some flow. Let's go that there's some flow coming in, maybe from rain into a reservoir. Okay, so this allows us to say that if I look at my control volume, I can then just write an equation directly, right from continuity. I can say that the rate of change of the volume in this tank, right, is just the flow coming in less the flow that's coming out. And let's say that that's Q0 here coming out. That's one equation. And remember, it's not a state equation yet because it's not in complete form. Now, this is an input, so we're done with that. And now we still need to determine what is this flow that's coming out. How does that depend on the possible states of the system? So you have to identify, at least in this system, that really there's only one dynamic state that we can have, and that's, we're choosing the volume because that's, remember, the state for a capacitive type element. You could have chosen height just as well. And remember that the height is related to the volume for this tank, at least through some constant area, right? At least for a constant area tank like this. So those are interchangeable. We just choose volume. And one of the reasons I like to say we choose volume is because it really is compatible with the dynamic equation that we use, which is the continuity equation, right? It's the rate of change of volume that's the difference in the flows coming in and out of the system, the flow rates, right? Those have units consistency. If you used height, then you have to deal with the fact that you're still going to have to write here h dot. At the end, if you want to write your equations in terms of height, that's easy enough. You just divide this everything by area, and then you deal with heights. But this is really more consistent with the way we write all of our equations. Okay, All right, so to finish this little model, we just need to find out what is Q naught. Well, we can just look at the model for this orifice here, and we need to decide how is Q naught related to the pressure difference across here, right? That somehow is going to be some function of the pressure at the bottom of that tank minus the atmospheric pressure, and that's A there. But we're using all gauge pressure, so we're just going to make it as a function of the pressure. So we need to find Q naught as some function of this pressure. And it turns out there's a very nice common relationship we can use, and we're just going to say that we have some discharge coefficient. Turns out that the square root, and we have to take the absolute value of the pressure here, right? And this is really only good for when the pressure is greater than or equal to 0, right? As soon as the pressure goes to 0, the model is no longer valid, right? So it doesn't make sense, at least in this case. The flow is not going to go back in the opposite direction if you have a negative pressure. So really this is only valid for positive pressures here. Because I can write pressure here as a function of height, and height is related to area, I can write this as rho g over height times area times the volume. This, in fact, here is 1 over the tank capacitance. Okay. Once I substitute this P into this equation here, I can then put it into this equation, and I'll have my final state equation. All right, so let's continue now, and just extend it to the cascaded tanks here. Sometimes I call this the 2 tanks problem, or even 2 cans. We do this sometimes in the lab. Let's call this number 1 and this number 2. The only difference between this one now is, of course, we have a second volume. So let's go ahead and call the volume here volume 2. This is volume 1. The flow now coming out of can 1, let's call that Q1. This guy is Q2. So really, this is just an extension of the previous problem. You should be able to directly show that, well, the rate of change of volume 1 is really just the same as we had over here, Q. Now it's Q1. We'll use this relationship here, and so we'll write that that's just negative K, and let's use 1 to correspond to the coefficient for that first valve or orifice, times the square root of, as you can see, that would be the absolute value of 1 over C1 times V1. You could absorb all of these into this K here, but that's the first equation. Note that this first one only depends on the variable V1 because you can't, basically, this first can doesn't know that the second can is here. However, when you write the equation for the second can, rate of change of the volume in this can or tank is Q is equal to the flow coming in, Q1, which is the one leaving, so that's a positive, minus Q2, right? So this term is exactly this term, right, except with a positive sign. And Q2, I hope you can see, it looks exactly like the one above, except it's got different coefficients. So you get a very nice simple set of equations. Very quick and easy.